Jai Hind students, welcome to this news episode. We have already started with the fresh topic of refraction of light, and in the previous lecture we have discussed these three topics in detail. We have discussed regarding the phenomena of refraction of light. It is basically the phenomena of bending of light or the phenomena of change in the velocity of the light whenever light travels from one medium to another medium. That we have discussed. Then we have discussed laws of refraction as well. Snells Law, which states that the ratio of sine of angle of incidence, Snells Law, this is very important. It states that the ratio of sine of angle of incidence to the sine of angle of refraction is constant, and this constant is known as refractive index of the medium. And what was the second law? Incident ray, refracted ray and the normal at a point to the interface all lie in the same plane. So these 2 points are collectively known as laws of refraction, right? Then a very important topic, refractive index. This we have discussed under 2 headings. One is the absolute refractive index, the other one is the relative refractive index. Refractive index of any medium, if it is kept in air or vacuum, then it will be the absolute refractive index. And absolute refractive index is defined as ratio of the velocity of light, absolute refractive index. It is defined as the ratio of the velocity of light in air or vacuum to the velocity of light in that particular medium, right? And I have told you, absolute refractive index of any medium is always greater than 1 because C is always maximum. Light travels with maximum speed in air or vacuum, which is 3 into 10 raised to 8 meter per second. This is constant. But as light travels in some other medium, its velocity decreases. When it travels in a denser medium, its speed decreases, right? More the denser the medium is, the lesser will be the speed of light in that particular medium. Then we have discussed relative refractive index. Relative means, suppose glass is placed in water or glass is placed in some other liquid solution like carbon disulfide solution. No air, no vacuum is involved. So in that case, the refractive index of one medium with respect to other, that is known as relative refractive index. And that is also defined as the ratio of the speed of light in first medium divided by the speed of light in the second medium. And students, in the previous lecture we have also discussed refractive index in terms of wavelength as well, right? So in terms of wavelength, it is defined as lambda air divided by lambda medium. This also we have discussed. So I hope these 3 topics are pretty clear, right? Let's discuss this one, factors on which the refractive index depends. As I have told you, refractive index of different medium is different. For air or vacuum, it's considered to be 1. For air, actually it is 1.0008, so it can be considered to be 1, right? For water, as stated, it's 4 by 3, 1.33. Refractive index of glass with respect to air, that is 1.5. Refractive index of diamond, that is 2.42. What I mean to say is that refractive index of different medium is different. Students, look, density of different medium is different. So refractive index does depend upon the density, does depend upon the nature of the medium. The more denser the medium is, the more is the refractive index of that particular medium under consideration. So factors on which refractive index depends. So first one is, it depends upon, refractive index of a medium depends upon the nature of the medium. It depends upon the nature of the medium. Different medium will possess different refractive index. So it does depend upon the nature of the medium. Not only this, student, it will also depend upon the nature of the surrounding medium in which this medium is placed. So it depends upon the nature of surrounding medium. What I mean to say is that suppose this is a glass slab placed in air. So refractive index of glass with respect to air, it is 1.5, right? Suppose this is glass, it is placed in water or some other medium. In this case, refractive index of glass with respect to water would be different. It would be different. And that can be evaluated. So what I mean to say is that not only refractive index depends upon the nature of the medium, but it also depends upon the nature of the surrounding medium in which it is placed. Or collectively, you can combine these 2 points. You can state that refractive index depends upon the nature of the pair of the two medium. Nature of the pair of the two medium. Right? The actual medium whose refractive index is to be determined and the medium in which the first medium is to be placed. So it depends upon the nature of both the medium. Third, it depends upon the wavelength. It depends upon the wavelength of the light. It depends upon the wavelength. Look, there is a relation known as Cauchy's relation. It relates the refractive index of a medium with the wavelength. The formula is A plus B by lambda square plus C by lambda 4. This is known as Cauchy's relationship. Now, with the reference of this particular relation, we can easily conclude a basic fact. The greater or the longer the wavelength of a given radiation, the smaller will be the refractive index of the medium for that particular wavelength. So what I mean is, a given medium will have different values of refractive indices for different wavelengths or for different colors. Different wavelengths means different colors, right? I'll explain it in detail. Students, you all are aware of the constant colors of white light. It is vibgyor, violet, indigo, blue, green, yellow, orange, red. So when white light splits into its 7 constant colors, that is vibgyor, V-I-B-G-Y-O-R, vibgyor. Wavelength of red is maximum and violet is minimum. This is known as visible spectrum. It is known as visible spectrum. And wavelength for violet is minimum and wavelength for red is maximum. So make use of this. Wavelength of red radiation or red wavelength is greater than wavelength of violet. Therefore, using this relationship, what do you get? Refractive index of the medium for the red color would be less than the refractive index of the medium for the violet color. Understood now? So what I mean to say is that same medium, I think a glass slab, when different wavelengths are incident, monochromatic beam are incident, red light, then orange, then blue, then violet, green, the same medium, which is glass in this case, will have different values of refractive index for different colors, for different wavelengths. The refractive index of glass for red radiation would be minimum. The refractive index of glass for violet radiation, violet color, would be maximum. That is what I mean to say. So refractive index depends upon the color of the radiation. That is, it depends upon the wavelength of the radiation. Understood? So students, these are the 3 factors on which the refractive index depends. Again, I must repeat it. Refractive index of a medium depends upon its nature, depends upon its own nature. Second, it depends upon the nature of the surrounding medium in which it is placed. Third, refractive index of a medium for different wavelengths, for different colors is found to be different. So from there we can conclude that refractive index of a medium does depend upon color of the radiation, does depend upon the wavelength of the radiation. For red radiation, the refractive index of a given medium would be minimum. For violet radiation, the refractive index of a given medium will be maximum. Right? So these are the 3 factors on which the refractive index of a medium depends. Now students, after finishing the topic of factors on which the refractive index depends, let's discuss the other one. Rules of bending of light. We have done this as well. So now let's discuss rules of bending of light. So let's consider rule 1. Suppose this is the interface. This is medium 1, this is medium 2. This is suppose rarer medium, and let us consider this to be denser medium. Right? So this is the normal. At this point we need to study refraction. So light is to be incident at point O in an oblique direction. This is the oblique direction. This is the incident ray. The angle which the incident ray makes to the normal would be the angle of incidence. This is the angle of incidence. Now look, if medium 2 is considered to be absent, then light, as per the rectilinear propagation light, would have travelled along the same straight path. But here, since light is travelling from one medium to another, that is from rarer to denser, it bends, and in this case it will bend towards the normal. The light will bend towards the normal. This is the normal, this is the normal. So it will bend towards the normal. And the angle which the refracted ray makes with the normal, it is known as angle of refraction. So from the diagram it is pretty clear that angle of refraction is less than the angle of incidence. We can easily verify this. Let's try to verify it, right? So this is rarer medium. Suppose here the speed of light is v1 and in the denser medium the speed of light is v2. Students, I have told you a very basic fact. Speed of light in rarer medium is always greater than the speed of light in the denser medium. So what I mean to say is that v1 is greater than v2, right? v1 is greater than v2. Therefore, v1 by v2 would be greater than 1, right? Also, v1 by v2 is equal to refractive index of the second medium with respect to first medium, like this. And refractive index is given by sin I divided by sin I. As I told you, it is read as refractive index of medium 2 with respect to medium 1. Right? It is to be considered in which medium the angular refraction lies. If the angular refraction lies in the second medium, then on applying Snells Law at point O, we will write refractive index of medium 2 with respect to medium 1. Now look, it implies that sin I is greater than sin R, which further implies that angle I is greater than angle R. So it's verified, angle I is greater than angle R. So students, rule number 1, whenever light travels from rarer medium to denser medium, then the refracted ray tends to bend towards the normal. Or in other words, the angle of refraction in the denser medium is less than the angle of incidence in the rarer medium. So that's rule number 1, and this is the mathematical verification of it, right? Okay. Rule 2. Now what to do is, let's interchange the medium. Suppose in this case, this is medium 2, or rather, suppose it's considered to be the denser medium, and let us consider this to be the rarer medium. Let's consider this to be the interface AB. This is the point where the refraction is to be studied. So what to do? The first step is to draw a normal. Normal is any imagined line which is perpendicular to the interface. This is the normal. Then light needs to get incident at point O in an oblique direction, not normal direction, in an oblique direction like this. This is the incident ray. The angle which the incident ray makes to the normal, that's angle of incidence. In this case, the light is traveling from denser to rarer. So in such a case, when light travels from denser medium to rarer medium, the ray bends away from the normal. In the absence of the medium, it would have travelled along the same straight path. But in this case, light is travelling from denser to rarer. It will bend away from the normal. So this is the refracted ray. This is the angle which it makes with the normal. So here this is the angle of refraction. So it's pretty evident over here, angle of refraction in the rarer medium is greater than the angle of incidence in the denser medium. Right students? It's simply the vice versa of rule 1. Rule 1 is rarer to denser, the refracted ray tends to bend towards the normal. Denser to rarer, the refracted ray tends to bend away from the normal. In this case, when the light is traveling from rarer to denser, the angle of refraction is less than the angle of incidence. In this case, when the ray of light is traveling from denser to rarer, the angle of refraction is greater than the angle of incidence. Right? Here also you can easily justify. I mean, over here it is V1 and suppose it is V2. In this case, which velocity will be greater? V2. Students always remember, speed of light in rarer medium is always greater. In the denser medium it is always less. So this is considered the rarer. I have interchanged the medium, isn't it? Now this is rarer and this is denser. So here V2 is greater than V1. Right? So therefore V1 by V2 would be less than 1. Earlier it was greater than 1. In this case it would be less than 1. So refractive index would be less than 1 and therefore sin I divided by sin R would be less than 1, which implies that sin I is less than sin R, which further implies that angle I is less than angle R. So it's mathematically verified. So in this case, when the light travels from denser medium to rarer medium, the angle of refraction is greater than the angle of incidence. Right? There is third one as well. It's not a rule, but do remember it. This is suppose the interface and this is the point, and there is a normal over here. This is suppose medium 1 and this is suppose medium 2. It is an oblique direction. Now what happens when the ray of light is incident normally? This is the incident ray. So this is known as normal incidence. It is known as normal. Normal means 90 degree for normal incidence. So what is the angle which the incident ray makes with the normal? Yes students, what is the angle which the incident ray makes with the normal? It's not 90 degree, it is 0 degree. Normal and this is the incident ray. Both are coinciding. So the angle which the incident ray makes with the normal is 0 degree. So angle of incidence is 0. So here angle of refraction is 0. So it will remain undeviated. So what I need to say is that, again, a very, very important concept. When ray of light is incident normally on a transparent refracting medium, then the ray of light won't get deviated. It will remain undeviated. So in this case, there is no bending of light, no refraction takes place. Refraction takes place only when ray of light get incident in an oblique direction other than 0 degree, right? In an oblique direction. Then only it tends to get bent either towards the normal or away from the normal. So in the third scenario, when the ray of light gets incident normally means making an angle of 0 degree with the normal, that is angle of incidence is 0. So in that case angle of refraction also becomes 0. So in that case the ray of light remain undeviated. So no refraction whatsoever will take place in this case. So student, I hope you have understood this concept. This was a very, very important concept. So we have discussed all these 5. Refraction, laws of refraction, refractive index, factors on which the refractive index depends, and obviously the rules of bending of light. Right? We'll discuss some another very important concept. We can discuss the principle of reversibility of light. Also students, you need to understand to apply Snell's law. That also I will tell you, and after that we can discuss the principle of reversibility of light. Right? Let's consider 2-3 cases. Right? Case 1. This is medium 1, this is medium 2. Indication of this arrowhead is very, very important. Suppose this is rarer medium and let us consider this to be denser medium. So obviously it will bend towards the normal. This will be the angle of incidence. This will be the angle of refraction. isn't it? And this is the normal. This is the normal. So, at point O, if you apply Snell's law, now in this present scenario, I am trying to convince you how to apply Snell's law, right? If you apply Snell's law over here, it will be ratio of sine of angle of incidence to the sine of angle of refraction. It is equal to refractive index. Now, refractive index of which medium with respect to which medium? Right? That is to be understood. For that, simply remember my wordings. You need to check that in which medium the angle of refraction lies. In this case, the angle of refraction lies in the second medium. So, it will be refractive index of medium 2 with respect to medium 1. Again, I must tell you, during the refraction, just check in which medium the angle of refraction lies. So, applying Snell's law, you will write sin I over sin r is equal to refractive index of the medium in which angle of refraction lies with respect to the medium in which incident ray travels. So, that is how Snell's law is written. Clear? For example, this is glass and this is suppose water. This is water and this is glass. Let's consider this another example. This is the normal over here. This is the incident ray. Indicate the arrow. So this will be the angle of incidence. So out of glass and water, obviously glass is a denser medium and water is a rarer medium. So light is traveling from denser to rarer. It will bend away from the normal. So it will be like this. It will bend away from the normal. So this is angle of refraction. So now if you apply Snell's law at point O, what you get is sin I divided by sin r. Students, look, here angle of refraction is lying on water. So it will be refractive index of water with respect to the medium in which incident rays travel, that is glass. So this is how Snell's law is applied. Again I repeat, you need to check the medium in which angle of refraction lies. So the refractive index would be the medium in which the angle of refractive index lies with respect to the medium in which the incident ray is traveling. Right? This is how the Snell's law is applicable, or this is how the Snell's law is mathematically expressed. Right? So, let's deal with the principle of reversibility of light. So, let us discuss this. Principle of reversibility of light. It's a very, very simple concept actually. Now look, let's consider this to be an interface. This is suppose medium 1. It's considered to be the rarer medium. Let us consider this to be medium 2. It's considered to be a denser medium. Right? This is a denser medium. Water or any other medium. What you do is, suppose we draw a normal over here. And ray of light is incident, like this. So this will be the angle of incidence, right? Ray of light is travelling from rarer to denser, so it will bend towards the normal. This will be the angle of refraction, no doubt regarding this. And here, suppose a plane mirror is placed. Here, suppose a plane mirror is placed. This is a plane mirror. This is suppose a plane mirror. And the light gets incident normally over here. It is getting incident normally over here. So this, students, we have already discussed in reflection of light. When light gets incident normally on a plane mirror, then what happens? It will get reflected back and it will retrace its path in the opposite direction. So this is path 1. This is path 1. Like this. This is path 1. And after getting reflected, here angle of incidence is 0 and angle of reflection is also 0. So it will get reflected back. This is path 2. This is path 2. This is path 1 and on getting reflected, it will retrace its path in the opposite direction. This is path 2, right? So what to do is, we will apply Snell's law for path 1 as well as for path 2, and we will come across a very important result. Again, I repeat, students, we are discussing the principle of reversibility of light. So what you have considered is, this is an interface separating two different media. This comes to be rarer and this comes to be denser, right? Let this be water, this be air. So when light gets incident in an oblique direction, and if it is traveling from rarer to denser, it will bend towards the normal like this. Now suppose a plane mirror is placed in such a manner that this ray get incident normally on the plane mirror. Normally on the plane mirror means angle of incidence will become 0. So the angle of reflection will also become 0. So after getting reflected, this is path 2. It will retrace its path in the opposite direction. Fine. So light is made to reverse its direction after getting reflected from this mirror. So for path 1, let's apply Snell's law. What do you get? Sin I divided by sin I. Ratio of sine of angle of incidence to the sine of angle of refraction is constant, and that is refractive index. Now students, how to write this refractive index? Again I must repeat. Angle of refraction is lying in the medium 2 and incident ray is travelling in medium 1. I am considering path 1. So it will be refractive index of which medium? Of the medium in which angle of refraction lies. With respect to which medium? In which the incident ray travels. So this will be the first equation. Clear? Now apply Snell's law for path 2. We are dealing with this particular path when it is retracing in its opposite direction. So again apply Snell's law at point 2. Now when the light travels along this path, so this will be the incident ray and this will be the refracted ray. This will be the angle of incidence, this will be the angle of refraction, right? I am dealing with this particular path, path 2. So this is incident ray, this is refracted ray. So in this case, sine of angle of incidence divided by sine of angle of refraction. This is the angle of incidence, this is the angle of refraction. It will be equal to refractive index of, for path 2, this is the angle of refraction. So it lies in medium 1. So it will be refractive index of medium 1 with respect to medium 2. Clear? So what we have done is, we have obtained two equations by using Snell's law. One is for path 1 and the second one is for path 2. Now multiply these two. Multiply these two equations. What you get is sin I divided by sin I multiplied by sin I divided by sin I. It will be equal to mu 2 1 multiplied by mu 1 2. So it is 1 mu 2 1 multiplied by mu 1 2. So we get a very important result. So mu 2 1 is equal to reciprocal of mu 1 2. This is a very important concept, right? So refractive index of medium 2 with respect to medium 1 is equal to reciprocal of refractive index of medium 1 with respect to medium 2. I'll give you some examples so as to clear the concepts. So basically, what's the principle? What's the statement then? The principle of reversibility of light states that if the light is made to suffer any number of reflections and refractions, and if its final path is made to retrace, if it is reversed, then it will retrace its path in the opposite direction, following the same path but in the opposite direction. And this is basically the consequence of principle of reversibility of light. Right? So what is the statement of principle of reversibility of light? If the light, after suffering any number of reflections or refractions, has its final path reversed, then it tends to retrace its path in the opposite direction. That is what we have discussed over here, and this is the consequence of principle of reversibility of light. Now, refractive index of glass with respect to air, this is absolute refractive, it is 3/2. So what will be the refractive index of air with respect to glass? It will be reciprocal of this. Just now we have discussed. So it will be equal to 2/3. Right? Another example. Absolute refractive index of water is